All right, so what you're going to be learning about in this presentation is how we got from nothing to the modern periodic table. So tracing the historical development of that process. So a number of elements have been known since ancient times, particularly those ones that have kind of unusual seeming symbols. Those symbols have Latin roots, so things like gold, which would be aurum, lead, plumbum, silver, argentum, mercury, and any number of others. The whole concept of the element actually dates back to the ancient Greeks, though, which, and Plato is actually credited with stating the idea of an element as an extension of what Aristotle said, that all matter is composed of earth, air, fire, and water. Remember, we talked about that when we discussed atomic theory. It took a long time after the ancient Greeks before elements were actually discovered in the laboratory. And the first person actually who discovered an element in the lab was a guy by the name of Hennig Brand, and he was actually an alchemist. And for those of you who don't know much about alchemy, alchemy was actually the science of the Middle Ages, and it was kind of a mixture of chemistry and physics and magic. And really what people were trying to do was turn base metals into gold, and they were trying to develop processes to do that. Now, they never were able to turn base metals into gold, but along the way, they made a lot of important scientific discoveries, and a bunch of different chemical elements were part and parcel of that, some of those discoveries. Anyway, Brand discovered phosphorus, and he actually distilled it from his urine, so he took the P out of P. And he kept that whole thing a secret until Robert Boyle actually rediscovered it. And Robert Boyle actually redefined elements as using the definition that we've learned. And an element is a substance that can't be broken down by ordinary chemical means. Okay. So that's what defines something as an element. Okay. So once all these elements started to be discovered, over time people started to think that there needed to be a system to organize them. And the first attempt was made by Lavoisier. In the late 1700s, he published what's considered the first chemistry textbook. And it sorted all of the elements that were known at the time into two groups based on their metallic or non-metallic character. Not a great way of sorting, but it was an early first attempt. Okay, and probably about 30 years later, Johann Dobereiner is credited with stating what's called the law of triads. And what he did was he took elements that had similar properties and he organized them into groups of three. And what he found was the middle element, landing in those groups of three, had not only an atomic mass, but properties that were almost an exact average of the two that it fell between. So if we're talking about this group right here, which is group 17, these are three elements right here, those would be chlorine with atomic mass of 35, bromine with atomic mass right around 80, and iodine, which has an atomic mass of 127. And if you notice, if the 80 kind of falls, is an average of 35 plus 127, give or take a little bit. And bromine kind of has intermediate properties in between chlorine and iodine. So continuing with attempts at organization, in 1865, John Newlands, who was a British chemist, sorted the 56 or so known chemical elements into 11 groups based on similarities in their physical properties. And what he saw was a trend that was kind of called the rule of 8 or the law of octaves. And what he saw was that about every 8 element, there were similarities in trends and properties. At the time, it really wasn't considered a huge deal, but that rule of 8 or the law of octaves becomes very important when we talk about chemical bond theory. So we'll be talking about that more soon. Also at that time, people began to notice what's called periodicity when they were developing their organization system. And a French chemist, his name Conquertois, was the first to notice this trend. And what basically periodicity means is that when you take elements and you arrange them in order of increasing atomic weight, which was what they were using at the time, there was a trend in similarities. So similar elements were occurring when at regular routine intervals when you ordered them by their atomic weight. And that trend is still observed in the modern table. It's something called periodic law, and we'll get to that a little bit more later. Okay, but periodicity, pretty important. In 1869, Dmitry Mendeleev published what is considered the first modern table. Now, that organization system that he developed looks way different than the table that we have today. And we know that the table we have today is sorted into metal, metalloid, non-metal, that there are columns that are called groups or families. There's 18 of them. There's 7 rows on the periodic table called periods, and that there's a couple series at the bottom. Now, his system doesn't necessarily look like that. First of all, there weren't 118 elements. There were about 65. But you still see some elements of his design in the modern table. So there were some good things about it. He took elements and he arranged them in order of increasing atomic mass as you go across rows and down columns. And it's the first time anybody's system kind of had a dual relationship there. He thought that physical and chemical properties of elements were probably related to their atomic mass, not their chemical behavior. And using that, he put similar elements in the same row on his table. And we'll look at what that looks like in a minute. His system allowed him to predict on elements that hadn't been discovered yet because he saw big jumps in atomic mass, or in the atomic mass pattern, so he left gaps for those. Okay, so that was what was good about it, and we see that, for the most part, his pattern is tested and true. What was not so great? Well, first of all, he didn't anticipate that there would be unreactive elements like the noble gases. And so he didn't leave space for them because he had no idea that they existed. So when they were discovered, his system had to be modified to account for that. The second way his system is not so great is there wasn't really a clear location for hydrogen. It actually went in a couple of spots. So it wasn't located specifically where it is now at the top of group 1 in the upper left-hand corner. Okay, so what we're looking at here is an example of what Mendeleev's table looked like, at least his first, at least an iteration of it. Now, this is not the original one that he published. This one started, he had done some tweaking. And what do we notice when we look at this table? Notice that some atomic symbols are different than what are used today, and that the noble gases are entirely missing. You can also see places where he predicted there would be elements discovered. That would be with these dashes that he left, and I'm just going to circle a few. There are a bunch of them throughout the table. Okay. A couple of things that you should also notice when you're looking at his system here is you see elements that are still in the same column today, on the table, close to each other. So there's hydrogen, lithium, sodium, and potassium, rubidium. There's some other cesium. There's some elements that aren't included in group 1 there as well. You should also notice that for the most part, period 2 of the periodic table, so period 2 is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. That row, for the most part, is still intact. It's right here. So you can see some of the grouping that we still use evident when you look at his table. Okay, so the first change to the table had to do with noble gases being discovered, so a group was added for them. The second big change had to do with when we started to learn more about the structure of the atom. And that second change led to a resequencing of the table. And that discovery had to do with the atomic number concept. So what Moseley discovered is that there's a relationship between an element's X-ray wavelength and its nuclear charge, or in other words, how many protons are in the nucleus. And what he did was he resequenced the table to be based on this value, not atomic weight. And his work, like Mendeleev, showed that there were gaps where there were some undiscovered elements. And he left blanks for them, and lo and behold, there were things discovered or elements discovered that fell into those blanks. The next major change to the periodic table happened in the 1940s, and that change was made or proposed by Glenn Seaborg. And Glenn Seaborg is probably known for, he's won 2 Nobel Prizes, known for discovering or building more elements than any other person. And he worked with what are called super heavy elements. And he saw that these super heavy elements kind of had unique properties, and that they didn't mesh well with the kind of the structure of the modern table that was developing. They really kind of morphed it and stretched it way out. So he thought that they would work better in separate series below the table. And so that's what those 2 separate breakout rows are. And they're called the actinide and lanthanide series. So we're finally at pretty much what the modern table looked like. We know that elements are regularly and routinely discovered, so the table does get changed and modified. But for the most part, the structure itself hasn't changed super significantly recently. But we do know that scientists are working pretty actively to build new elements. The modern table, as did Mendeleev's table, follows what's called periodic law. Mendeleev's table said that when you take elements and you organize them in order of increasing atomic mass, patterns are going to repeat at regular intervals. Well, the modern table says, or periodic law according to the modern table says, that when you take elements and you arrange them in order of increasing atomic number, patterns are going to repeat at regular intervals. Regardless, that's what periodic law says. Okay? So what we're going to start looking at in class is, what does it mean to follow periodic law? What are some properties that follow it? And we'll be researching some particular properties and learning about some bigger trends on the table by applying those properties.